the example I showed you in this previous slide, the concentration of aluminium, what species aluminium was, depending on the pH, is what we call a single variable diagrams. And it's a diagram that we use mostly and quite effectively in an environmental context, but you can apply it in all sorts of things. That shows you how your a particular compound or a particular element you're interested on changes depending on the proportion of that compound, changes depending on whatever your variable you are studying. And it could be, for example, the most common one, or the one we're going to be using here, is the pH diagram. So it's a diagram in which it tells you for a particular species that you're interested, a cadmium ion, carbonate. Well, I will show you several examples in future slides. How it changes. You have these species that you're going to call X, and how it changes as pH increases. How the concentration it changes at different pHs, and you have all sorts of shapes. For example, you could have something like this. They have different. It can have different shapes depending on the behavior of that species, and that allows you to track at any pH you can think of what is the proportion of that compound in that particular form in the environment. pH diagrams are very popular because, well, they're very easy to construct, and I will tell you in a second how you can make them. And you can very easily get information about this particular species, a particular chemical compound, or an ion or cation in a water sample, but just by measuring the pH of the sample, which is a very simple measurement to take. And when I say they're very easy to construct, is because you don't need data from the field. You just need to know the acidity constant. The acidity constant is a base of that compound. You need all these equilibrium constants for that compound, and that's the only thing you need to construct the diagram. I've made this one for acetic acid. This is the information of the acidity constant for acetic acid. And the pKa of acetic acid minus log of the acidity constant is, give or take, 4.8. Specifically, I think it's 4.76. And if you click on this slide in the module Blackboard, you will see that this is an Excel file, and it will open this file I've got here that I'm showing you. So what does it tell me? Well, if you have acetic acid, I'm going to call it HA. We don't care about the structure of this acetate. And you dissolve it in water, then it's going to liberate hydrogen ions and acetate anions. So if the water is neutral, then most of the hydrogen ions will come from the acetic acid. But if you have water that is acidic or basic, so if there are already hydrogen ions in the medium from other sources, from other bases and other acids dissolved there, then that's going to affect the dissociation of my acetic acid, because you will have more hydrogen ions in solution, not only the ones that come from the acetic acid. So what does this diagram tells me? It tells me at pH 0, so a very acidic pH, all my compound will be 100%, fraction 1, will be acetic acid. That's the blue line. When the pH increases and we reach somewhere around 3, then I'm starting to have a little bit of, okay, that means that there are not that many hydrogen ions there are slightly fewer hydrogen ions because the pH is increasing, so we are moving towards a more basic pH, and the reaction of the acetic acid dissociating to produce hydrogen ions start to take place. So you start generating the acetate anion, and that's where the red line appears. And in total, it has to add to 100. In total, the amount of acetic acid and acetate has to add up to how much acetic acid you started with. But the proportion of how much will be acetic acid and how much will be acetate will change depending on how many hydrogen ions are already in that solution. When you reach the point of pH around 4.8, 4.76, then you have the same amount of hydrogen ions of hydroxyl ions, 50-50. When you move to higher pHs, about 4.76, around 4.8, then the amount of acetic acid starts decreasing, and the amount of acetate continues increasing until slowly you reach a pH around 7 or something like that, in which all your acetic acid in that solution at that particular pH will be in the form of acetate. And for the case of the acetic acid, it's not particularly important, but if you have a species in which if you have a compound in which one of the forms is more toxic than other, then just by measuring the pH, you will know how much of each of the forms of the compound you're interested on is actually in solution. And I've got a few examples in the next slides. You can establish a pH diagram for a diprotic acid or a triprotic, any number of hydrogen ions that can be donated. And the method is the same as the previous one. It's just the graph becomes more and more complicated because you start having more species in solution depending on the pH. In the case of carbonic acid, you have two acidity constants, two hydrogens that can be donated. So you have a total of 3 species that you can have in solution, or a mixture of them. You can have carbonic acid, you can have the species hydrogen carbonate, or you can have the species carbonate. And depending on the pH, you will have a proportion, you will have one, the other, or a mixture of 2 of them at any given time. And what gives you where those changes are going to happen are the acidity constants, or better, the pKa's, the 2 acidity constants you've got. The pKa for the first acidity constant and the pKa for the second acidity constant, 6.4 and 10.3. And they are, give or take, here is the first one, 6.4, and here, 10.3 is the second one. So how do you read this graph? Well, at pHs lower than 6.4, you mostly have carbonic acid, which is the most stable species at the very, very low pHs. The CO3 totally protonated all the hydrogens attached to the CO3. When you start increasing the pH and you start moving around, you're getting close to the 6.4, then this reaction starts to take place. And then you start having a mixture of the carbonic acid and the hydrogen carbonate, which is that green line. At 6.4, you have 50-50, the same amount of one or the other. And then as the pH increases slowly, you start having less and less carbonic acid and more of the hydrogen carbonate, until eventually you reach a point in which you have no carbonic acid left. At some point, you start having the second equation in place. If you increase the pH, slightly your hydrogen carbonate starts reacting to produce the carbonate anion. So the carbonic acid has completely disappeared. Your hydrogen carbonate starts reacting to give you your carbonate anion, the second reaction. And you reach the point here at 10.3 in which you have 50-50 of hydrogen carbonate and carbonate anion. And the blue line represents the carbonate anion. And as the pH increases till you reach 14, the proportion of carbonate in the sample increases, and you have less and less hydrogen carbonate until it completely disappears. And at sufficiently high pH, the only species you have in solution is the carbonate anion. So that means that at any point here you can check, you can check the pH, say, pH 8. When am I going to have a pH 8? Well, at pH 8, all that I'm going to have in solution in terms of the carbonate equilibria is the species hydrogen carbonate. At pH 9, give or take around here, at pH 9, I will have actually two species. I will have the hydrogen carbonate and some carbonate. Most of it hydrogen carbonate, let's say around 90% of it, and around 10% of the carbonate. And when you have many hydrogen ions, so an acid that can produce many hydrogen ions, then the diagrams are still the same. It just becomes more and more complicated in the sense that you add more and more species you can have depending on the pH. Phosphoric acid has 3 possible species. You can have phosphoric acid, you can have dihydrogen phosphate, you can have hydrogen phosphate, and you can have phosphate. So there are 4 species. And the different pKa's of this reaction will give you the different cutoffs for how the different species transform from one to the other. So at any given point, you will be able to know if your species if your phosphorus is in the form of H3PO4, phosphoric acid, which is the red line. If your your phosphorus is in the form of dihydrogen phosphate, which is the yellow line. If your phosphorus is in the form of hydrogen phosphate, which is this blue line, or if your phosphorus is in the form of phosphate, which is the purple one, or if you're going to have a mixture of a couple of these species, and which ones are going to be, and in what proportion you're going to have them, considering that all of them will, in total they have to add to 100 or to 1 if you're doing it as per 1 rather than per 100.